The standard decision tree model is rather simple. And because it is rather simple, it's only going to perform so well. To get a better performing model, we can create ensemble models, ensemble estimators using this standard decision tree model. Create a more complex model using a single decision tree to expand on it. Ensemble estimators, ensemble models, are simply models that are going to use more than one estimator, more than one predictor, to arrive at an answer. There are three different types of ensemble models. There is the bagging, the boosting, and the blending models. We saw blending previously in a different lecture, and what blending refers to is you can take different machine learning models, take the predictive value, and learn how to best blend those models, best blend the predictive values of those models. In that situation, the predictive values for the individual models become features in a downstream model that learns how to best blend the model's predictions. In other words, perhaps you have two models, K and N, and decision tree. Then you train a linear regression model that learns the weights, how to best contribute the different models' predictive values. Perhaps, in this example, K and N does a better job, then it makes sense that you're going to contribute more, you're going to add more weight to the K and N's value, its predictive value. That's a blending. You're blending the results of several machine learning models. For decision trees, people have used decision trees to construct bagging and boosting models. We'll discuss each of those in a bit. The first model, the first ensemble model using decision trees that we're going to discuss is random forests. Let's first discuss the situation. Let's say I really want to know, I want to get a good idea about some process. Let's say I want to get a better idea of how the markets will perform in the coming year. I could go just to the street and pick a random person. Pick a random person and ask him or her, what's your opinion how the markets will perform in the coming year? Well, if I do that, do you think I'll arrive at a good answer? I might arrive at a good answer. Maybe I just happen to be lucky and ask someone that's very knowledgeable in this field and they give me a pretty good answer. In that situation, I was rather lucky. But understandably, I'm going to probably ask a lot of people who may not have a good idea of this subject, may not provide me a good answer. But I understand that there is wisdom in the crowd. And so instead what I can go ahead and do is let me ask a wide range of people, a diverse set of people, and ask them for their opinions. So these opinions will vary across the board, but I'm going to get a diverse set of opinions, diverse set of answers. And I'm less susceptible to the randomness of just picking one or two people. So by using the wisdom of the crowds, by pooling all their answers, their responses, ideally I can give a pretty good answer, a pretty good prediction of how well the markets will perform in the coming year. I can do a very similar thing, a very similar idea for decision trees. Instead of relying on one decision tree to arrive at an answer, let me rely on multiple of them. Let's say 10. Let me rely on 10 decision trees to arrive at an answer. If I'm doing classification, I can take all these 10 trees and see which class is most predictive. What is the majority class from the predictions? Let's say these 10 trees, let's say one class was predicted 8 times. Well, then that's going to be my answer because that was the dominant answer from all these trees. So I'm going to aggregate all the results of my individual trees. If I'm doing regression, what I can go ahead and do instead is take the mean of all the predictive values. Each tree is going to predict a different value, a different label. I can just simply take the mean, pull all those answers, aggregate them all to go ahead and give one final answer. So our idea there is that just relying on one might not be such a good idea, but I'm going to go ahead and average them out, pull them together, arrive at an overall a better answer. So I want to replicate this process for decision trees, but if I just take 10 trees and they're all trained on the same training data, and they're all trained exactly the same process, exact same way, then all I want to do is arrive at 10 trees that are exactly the same. 10 trees in which I would visualize them, how they look like. I see they're going to have the same depth, the same terminal nodes, the same leaves. They're also going to ask the same questions, the same yes or no questions to arrive at a prediction. But I don't want this. I don't want my trees to just be clones, to be identical of each other. There is no diversity there. There is no wisdom in the crowds. This is analogous to just going and asking a set of people, maybe I can ask 10 people their opinions about what's their prediction of how the markets will perform the next year. But if they all come within the same school of thought, then I'm just really in an echo chamber. I'm all going to get the same, roughly the same prediction. So I'm not really getting diversity. I'm not really exploiting the wisdom in the crowds in that situation. So I need to fix this situation. I need to fix this problem. I don't want trees that are all clones. Ideally, each tree in my forest, hence the name, a collection of trees or a forest, are going to be trained on a different training set. And this is crucial because I understand that training sets differ from each other, and I'm going to get a different tree. The tree is going to look different. Its structure is going to be different. It's going to ask different questions to arrive at an answer. So I want different training sets, but this is a lot easier said than done. So I have to make the best of my situation. So I only have one training set, and you consider a training set as a sample from a population. All the observations belong to a population, and I produce a sample from that population. I sample from that population, and that's my training set. And it's prohibitively too expensive to go back and sample more points from the population, because ideally each tree would be given its own training set. If it's given its own training set, then resulting trees will look different, because I understand there's idiosyncrasies in the training data. So I got to make the best of my situation. So what I got to do is I got to pull myself through the bootstraps, or with the bootstraps. That's an expression that refers to make the best of a given situation. I have only one training set, so let me do my best to replicate having multiple training sets. So one way to make the best of the situation, given what I have, this limited one training set, is generate new training sets through sampling with replacement. This is what, when you hear bootstrapping with regards to this, with statistics, this is what it means. We generate a new data set, a new sample set via sampling with replacement on the original sample set. The way you can view this process is we have our training examples in one bag. We put our hand in there, we pull a sample, we replicate that sample, we put that new sample or that sample value in a new bag, and we make sure that we replace it in the original bag. So it's still there. Because it's still there, what's going to happen is that I'm going to sample some observations more than once. Remember, the whole point of this process, the whole point of bootstrapping is I'm going to try my best to generate a new sample set that looks different, that is different from the original. Yes, they're going to be related because they all come from the same training values, but the idea of sampling with replacement, each training set is going to be different. This is my best attempt, my attempt to pull myself with my bootstraps. So now all my trees, I can give each tree a different training set. It's going to look slightly different. So then when I train each tree, the resulting trees will look different. If I will examine the questions they ask to make a prediction, they're all going to be slightly different. I'm one step closer to generating a diverse set of trees. But there are other ways I can generate a diverse set of trees. What happens if one feature is very dominant in this process? In other words, one feature is going to be used a lot to make splits. One feature is going to be used a lot in these questions to arrive at an answer. Will that hurt our diversity of our trees? Will that hurt the resulting diversity of my set of trees? Remember, one of the goals here is I want a diverse set of trees. I can achieve that by giving it each tree a different training set, but what would happen if a feature is very dominant? And it's going to often be chosen to make a split. If one of those features is very dominant and will oftentimes be chosen to perform a split, then our diversity of our forest is going to take a hit. The resulting trees are going to look very similar. So I'm not going to have a very diverse set of trees. Remember, I want a diverse set of trees. I don't want a monoculture. So one way I can fix this problem that there might be a feature that's going to be over dominant is perhaps when I perform a split on my tree, when I grow my tree, maybe only consider a subset of the features. Let's go back and how these decision tree models are trained. At each node, what the model is going to do is it's going to consider all the features and all the values for those features to figure out which one's a good threshold to use. What's a good question to use to best split my node? And by best, we discuss what are those metrics. For classification, it was Gini or entropy, and for regression, it was the overall drop in variance. But to prevent a situation where one feature is dominant and will always be chosen, or will be chosen a lot to perform splits, at each node, we're going to consider a subset of the features. Instead of, let's say we have 9 features, instead of considering all 9 features to decide which one is a good candidate to perform a split, let's just choose 3. Let's just choose a random 3. 3 random features. We want to only look at those 3 random features to decide at that point what's a good way to split this node? What's a good way to partition my space into 2? So now my resulting trees are going to be diverse, are going to look different from each other. So I can mimic the idea of the wisdom from the crowd, the wisdom of the crowd. So that's what random forest is going to do. Those 2 techniques is going to utilize to have a diverse forest. To avoid a monoculture, use bootstrapping to generate different training sets for each tree, and is going to only consider a subset of features for each node split to prevent a feature to over-dominate. You don't want your trees to be highly correlated. You want them to be uncorrelated. Now for random forest, let's discuss the hyperparameters that are involved for training this model. Those hyperparameters will be the same as before. So we'll have ideas like max depth and min sample split, min samples leaf. But with a random forest, there's some additional hyperparameters that we have access to. The most important one is the number of estimators. This just refers to how many trees make up our forest. Other ones are n jobs, and this is simply just, isn't going to really affect performance, is not going to affect the performance. It just says whether we want to run multiple jobs in parallel. Remember, training each of these trees can be done in parallel. It's an easily parallelized process, so we can set n jobs to a number that's not 1 and have a faster training time. There's also the warm start hyperparameter. If we set it equal to true, what's going to happen is that it's going to reuse to train trees from a prior fitting and just train additional trees. In other words, let's say you have a very small forest of 5 trees, and you look at your analysis and you realize, you know what? I want to use more trees for my model. I want to use more trees because only 5 trees isn't such a great idea. So let's say you want to train 5 additional trees. Well, what happens is if you set warm start equal to true, if you retrain that estimator, it says, okay, I already have 5 trees. There's no need to retrain those trees. Let me just train the 5 additional trees that you asked for. So you can, using warm start equal to true, you can grow your forest. You can grow your forest. You can grow it and not have to retrain the trees. For example, let's say you train 10 trees. You realize that's not enough and you want to train 20. You don't have to train 20 new trees. You just train the 10 additional trees. So it's going to prevent a lot of redundant calculations, can help us scale our estimators, scale our process. And one last thing about the random forest is that since it's going to rely on bootstrapping, it's going to aggregate the results, it's going to be called a bagging estimator. So bootstrap aggregation, we get the bagging ensemble model. The question that I pose here is that are there any other advantages of considering a subset of the features? We understand that considering a subset of the features are going to help the model generate a diverse set of trees, but are there any other benefits by only considering a subset of my features? As I grow my trees, as I'm creating node splits, if I'm only considering a subset of my features, then my training time complexity, my training time is going to be faster. Instead of considering 9 features to see which one's a good feature to use to perform the split, I only consider 3. It's going to run 3 times faster. And this is great because with the random forest, the model is going to take longer to train because now I have more than one tree in my model. So even though I'm using, let's say, 100 trees, instead of considering 9 features, I use 3, then yes, the model will take longer to train, but not by 100. So that's an additional benefit by only considering a subset of my features to perform a split. Let's go and analyze this random forest model. Let's see how it performs. So we're going to use a random forest regressor. We're going to have a function here to plot the resulting mean square root error for a random forest, and we're going to plot this as a function of the number of estimators we have in the model. So let's grow our forest, and let's see how this error changes as I increase the size of my tree. I'm going to use a test set error. Run this plot there. With my decision tree, there's additional hyperparameter, max features. And there, in one example, I'm going to use the square root, and the other one I'm going to use the log. So if I have 9 features, consider 3. Or I can take the log of base 2 of my features, only consider those number of features to perform my split. Typically, the square root does better, so it's a preferred one, but that's a different hyperparameter I have access to. I can go ahead and experiment which one will perform better. So this is how my plot looks like. Let's make sense of it. So the general behavior here is that as I increase the number of trees, my test set error is going to drop. In fact, there's a very sharp drop in error when we start initially growing our forest. So when we have a very small forest, we have a large error. When we expand our forest, as we grow it, there's an initial drop in error. And the general trend is that as we increase the number of trees, in general, performance will increase. But notice it's a little hard to tell, but it appears that you can overfit with a large number of trees. If I look at this plot, it looks like the lowest value occurs around 30, maybe 33 trees, closer to 30 than 40. And as I increase the number of trees beyond 40, the training set error does increase, but it doesn't increase too much. So yes, the take-home message, or one of the take-home messages here, is that as my forest grows, I can overfit the model. I can have an overfitted model, but it's rather robust to overfitting. In other words, that overfitting, the amount of overfitting that I get by having a very large forest is very small. And that's great because if I happen to have a very too large of a forest, then my performance isn't going to take a big impact. It's going to take a big hit. However, the downside of having a large forest is because it's going to take longer to train and longer to predict. So let's make sense of this behavior. Let's make sense of this overall trend where there's an initial big drop in error, but then it tends to plateau. Can we make sense of that? Why is that occurring for our random forest model? Well, let's go ahead and consider the situation of how this works. We're trying to get wisdom of the crowds. So what happens is that if I have a very small forest, when I include an additional tree, then you can think of the overall diversity of the forest is going to jump. And as I grow and grow as my forest grows and grows and grows, adding new trees are going to increase that diversity, but at a certain point, adding a new tree isn't going to really contribute to the diversity of my forest. Yes, that tree looks different than what I have initially, or what I have for my forest, but that new tree looks very much like some other tree I already have. So I'm not really contributing to the diversity of my forest. So in that situation, after a certain point, there really is we've sort of exhausted the number of possible trees, the number of possible distinct trees we can add in our forest. So adding more of these trees isn't going to really increase the model's performance. I'm just going to ask another person, and they're going to give a very similar answer to what I already had before. So that's why we have a very initial drop in error, but after a while we plateau.